final class. Last things. All right. So in PDE that is reduced to a system of ODEs by spatial discretization. And we would be particularly interested in a linear case where y prime is equal to some matrix A times y. But the first one covers the nonlinear case also. So last time I listed several methods that could be used to solve this kind of system of ODEs. Well, I want to recap that with a quick remark about where the methods come from. One-step methods, which is either Euler method or Runge-Kutta method. Designed by Taylor expansion. So, for example, in the case of Euler's method, y of t plus delta t, Taylor expansion is equal to y of t plus delta t y prime of t plus delta t squared over 2 y double prime of t, and so forth. So y prime, however, is equal to f. So y at time n plus 1 is equal to y at time n plus delta t f at time tn. And then everything else is neglected because it's ordered delta t squared, which is pretty small. And that's where Euler's method comes from. So all the one-step methods that I covered, Euler's method, forward or backward, doesn't matter which. They just use different Taylor expansions. Or Runge-Kutta methods, which use Taylor expansion for every stage, like those K1, K2, K3, etc. So it's multiple Taylor expansions. All are based on that idea to come up with one-step methods. And it's those neglected terms that lead to the error, but I'll talk about that a little bit later. And then the other kind were multi-step methods. Adams methods that come from the integral form of the ODE. If you integrate the ODE from time tn to time tn plus 1, so it's a definite integral, then you get this. That is exact. There's no approximation in here. But where Adam's methods come from is approximating this integral by some quadrature rule that goes further back in time. So prior to Tn. Notice the solution appears on both sides. It appears here in the integral, and that's unknown. So we had to approximate this. And then the other kind is backward differentiation formulas, BDF. And those use various numerical differentiation. So in other words, finite difference formulas to approximate the y prime. So those work with the original ODE. All right, so that's just a super quick summary of the methods that were presented. And because the thing is, it's helpful to know where these methods come from. What is the main idea in deriving them? Because when we come across the shortcomings that these methods have, then we can go back to that original idea and consider something else. Or consider some modification of that idea. Okay. Now, a quick pro and con. There's different types of methods. There's actually multiple ways of classifying methods. So I gave one classification right here. One step versus multi-step. Why would you use one versus the other? So multi-step more efficient than one-step methods. Both one-step methods and multi-step methods perform several evaluations of f in a time step. But multi-step methods are using evaluations of f from further back in time, meaning they've already been done. So multi-step methods, they only require one new evaluation of f in each time step. So in that sense, it's kind of like Euler's method, which evaluates f only once. Whereas Runge-Kutta method, like that fourth order one I wrote last time, requires 4 evaluations of f every single time step, 4 new evaluations. And there's some other Runge-Kutta methods that need even more. It's awful. So that's an advantage of multi-step methods. One-step methods, on the other hand, they can be used immediately. There are no starting values. Now, what do I mean by that? Take a multi-step method. All right, so multi-step method, let's say it's a 4-step method. So I'm at time 0, and I want to get to time 1. Well, multi-step method would require me to have information from time level -1, -2, -3. I don't have that. So multi-step methods cannot be used at all for those initial time steps. So if you have a k-step method, then you cannot perform the first k-1 steps because you just don't have the information. So what do? You perform a 1-step method first to get through those initial time steps until you build up enough information. Then a multi-step method kicks in. So, all right. So that's so in order to realize that efficiency gain from multi-step methods, you got to use you still have to partner it with a one-step method. Okay. All right. Now, okay, so that's one-step versus multi-step. Another way of classifying methods: explicit versus implicit. Now, an implicit method tends to be more work per time step, because an implicit method you have to solve for yn plus 1. You may have to use some iterative method, like Newton's method. You might want to perform more than one iteration of it. So each time step is pretty expensive computationally compared to an explicit method, which is just a straight plug and chug. On the other hand, explicit methods, for reasons that I will lay out for you in just a moment, they need more time steps. So in other words, the step size, the delta t, generally has to be smaller for an explicit method. Well, okay, unless it's my KSS method, but that's the other thing. Sorry, I have to get these digs in when I can. Mm-hmm. All right. So it's a question of and for certain PDEs or system ODEs, the time step restriction can be so severe that people think you're crazy to not use an implicit method, even though each time step is more work. Okay, so that's the rundown on the virtues of one kind of method over another. Okay. All right. These are the things I like to ask about on oral finals. The nice thing is you don't have to write anything on the board. Okay. Now, the other thing I need to take a little time to talk about are the essentials of error analysis, which are, if you'll forgive a pun, quite consistent with error analysis that we've already seen for time-independent problems, where I talked about consistency, stability, convergence. So all of those concepts apply here as well, and they have essentially the same meaning. Okay. So what does consistency mean for a system of ODEs? This is y prime equals f. Okay. So just like with Poisson's equation and similar equations, time-independent ones, you substitute the exact solution into the numerical method. All right. So the idea is, if we recall, yn is our approximation to the exact solution of y at time tn. So exact, numerical. So that means that, for concreteness, I'll consider a one-step method. A one-step method would have this form. Yn plus 1 is equal to yn plus delta t f, or actually some function I'll call phi that depends on tn, yn, and your time step. All right, so any one-step method, whether it's Runge-Kutta method or something simple like Euler's method, can be written in that form. Like for Euler's method, this would just be f. Okay, now, so this is the general case. Okay. Now, I can write this in a form that's similar to that of the original ODE. Okay. Now, so the numerical solution satisfies this exactly, but this is the approximate ODE. So in other words, this is yn prime, approximately. So now suppose I substitute the exact solution into this. Well, the exact solution is not going to satisfy this exactly. I'd have y of tn plus 1 minus y of tn over delta t is equal to this function phi of tn, y of tn, delta t. And since it will not satisfy this exactly, there will be something left over, which I'll call tau n. So what is this? This is the LTE. Does anyone remember what LTE stands for? Very good. Local truncation error. So exact same meaning, pretty much, as when we saw this before with Poisson's equation. Okay. Now, how do you get a useful expression for the local truncation error? What do you need to do to get the expression for this? It's what you've been doing in the homework, in your error analysis.
Find the order.
Yeah, to find the order, what do you do? Bingo, Taylor expansion. So that is all the same here. You're just doing a Taylor expansion in t instead of x. Okay. So what you would get is something times delta t raised to a power. So whatever that power is the order of accuracy. But finally, I can say what consistency is. So the method is consistent if the local truncation error goes to 0 as delta t goes to 0. Now, I laid this out for a one-step method, but the exact same thing applies for a multi-step method. The important thing, though, is you have to divide by delta t. That way, the numerical method is written in such a way that it resembles the original ODE. And that way, local truncation error is defined properly and consistency. Okay. All right. Now, as far as order of accuracy, what can be said about order of accuracy of the various methods that we've seen? So when I say order of accuracy, I mean that the local truncation error is order delta t to some power. Okay. So Euler, power is 1. Euler's method, forward or backward, doesn't matter. First order accurate. Okay. I think I've studied a couple trapezoidal methods. Is there certain Runge-Kutta methods? Those are second order accurate. I can say the same for midpoints. Both those are second order accurate. By the way, Sarah, for tomorrow's final, you know what trapezoidal midpoint method, those composite integration rules are second order accurate. It's the same thing. Okay. I described a fourth order Runge-Kutta method. I don't have to tell you what P is for that one. I hope not, anyway. So, now, what's interesting is the trapezoidal method has two stages. Actually, the midpoint method is also described in a two-stage way. Fourth order Runge-Kutta has, oh, I forgot, I missed an R. Fourth order Runge-Kutta. So P equals 4. Fourth order Runge-Kutta has 4 stages. Now, that might make you think that the order of accuracy of a Runge-Kutta method is always the number of stages. That is not always true. But yes, generally, more stages lead to higher order. Okay. Multi-step methods. So, okay, so an S-step multi-step method. Okay, I should make clear that is not a 5. It is an S. It depends on the type of method. An Adams-Bashforth method, the order of accuracy, P is equal to S. That's an explicit method. An Adams-Moulton method, P is equal to S plus 1, because you have an extra stage. You're evaluating F at time Tn plus 1 to make it implicit. So that extra evaluation of F gives you 1 greater degree of accuracy. And then finally, a backward differentiation formula, P is equal to S again. Okay, so that's an order of accuracy rundown of various methods I showed you. Okay. Now, so at least in the case of Euler, I want to give a concrete expression for the local truncation error. Okay. So, for forward Euler, the local truncation error is very easy to describe. All it is the next term in the Taylor series expansion. Delta T over 2 y double prime at some unknown time. So if we have an idea as to how big the second derivative of your solution can get, that gives an idea of how big the LTE can get. But the important thing is this, that it's delta t to the first power. And that's how we know it's first order accurate. Okay. Now, so one might think, with all these methods of different order of accuracy, why would you ever use a low order method? Because, if I have a factor of 10, Euler's method, the error will decrease by a factor of 10. Whereas with fourth order Runge-Kutta, it'll decrease by a factor of 10 to the fourth, 10,000. So why do we ever have low order methods? Here's why. The derivative. What if this derivative is particularly large, or what if it's not even defined? What if your solution only has so many continuous derivatives? The higher order of a method is, the higher order derivative. So like a fourth order accurate method would involve the fifth derivative. So those derivatives can get exceptionally large, or if especially like if a solution has some oscillatory character to it. Maybe a solution has some discontinuities, and so these derivatives don't even exist. So in that case, a high order method is terrible to use. So in fact, one of my colleagues at Stanford is, consistently prefers using low order methods for the kind of differential equations that she has to solve, because the solutions and the differential equations themselves tend to be very badly behaved. You just can't count those derivatives being there. So sometimes, depending on the problem, low order is better. Okay. All right. So
how would that affect if it's low order? I mean, it just may not be very accurate.
Yeah, or you may have to, in order to get a certain level of accuracy, it'll take more time because you got to take more time steps. Yeah, so just because that error is equal to a low order of delta t times something. So yeah, you can't get a solution as efficiently, but all that means is if that is a badly behaved ODE, maybe the only thing you could do anyway. You might try a higher order method and have it fail. So if things are generally well behaved, smooth coefficients, smooth solutions, things like that, you might as well use a high order. Yeah. Okay. So that's okay. Now I've only talked about local truncation error. There is global truncation error also, which is the error accumulated over all time steps. But there's not much to say about it really. That whatever order of accuracy the local error is, the global error will have the same order. So people to find out what is a local order and just go with that. So the other thing to think about, because with the previous discussion of Poisson's equation and error analysis, there was consistency that we had to establish, and what was the other thing that we needed? Stability. If you have the two together, you have convergence. Same thing applies here. So really it's just making sure you have both consistency and stability. And consistency is pretty easy to check. Now, so the last thing I'll talk about is stability.
Consistency and stability equals
convergence. Yeah, and that's the Lax equivalence theorem, which I stated for time-independent problems, but applies just as readily to this. That's what I've done in some of my papers, is a full convergence analysis, where I have a proof of consistency, proof of stability, proof of convergence. And really the proof of convergence is the least interesting one, because it just builds on the other two. Let me make sure I didn't screw up the recording. Hello? Okay. Oh, yeah. Okay. So, all right. So as far as stability is concerned, and I'm going to focus for simplicity on the linear case. Y prime is equal to AY.
And this is with stability.
Yes, now I'll talk about stability. All right, a little section header for your notes there. Okay, so if you look at forward Euler, then applied to this problem, it will look like this. Yn plus 1 is equal to Yn plus delta t a Yn. But that can be written as identity plus delta t a Yn. Similarly, I have backward Euler, Yn plus 1 is equal to yn plus delta t a yn plus 1. So what I can do is I can rearrange this and solve for yn plus 1, and it would turn out to be identity minus delta t a inverse yn. I glossed over the algebra, but that's something you can convince yourselves of. Okay. Really, I just took that last term, moved it to the left side, factored and multiplied by the inverse matrix. Now, if we go by traditional ODE, the solution is a matrix exponential. Now, if we compare the matrix exponential, EVAT, actually, I'll write it. Well, okay. I'll fill in delta t just for consistency. So the point is to take a time step with the exact solution, you multiply by e to the a delta t. Now here we do not have e to the a delta t, but can anyone tell me how this relates to e to the a delta t? Why can we say that that's at least an approximation?
Do you take the natural log of
No? So if I have e to the x versus 1 plus x, if I want to approximate e to the x by a polynomial, what polynomial could I use? What? Okay. All right. Or what? Or if I want to approximate e to the x around x equals 0.
3 to the x? No.
No. Taylor expansion.
10.
Yeah. These are the first two terms of a Taylor series for the exponential, and that's what we have here. Now, what about this one? Here we have the first two terms of a Taylor expansion of not e to the a delta t, but e to the minus a delta t, and then we take the inverse. So in both cases, so in general, we have yn plus 1 is equal to, let me check my notation here, some matrix M times yn, where M is an approximation of e to the a delta t. Now, if it's like a, if it was a Runge-Kutta method, it'd be a much more elaborate approximation than this. It'd be like a higher degree Taylor polynomial, if you will, or something, or higher degree polynomial that matches a Taylor expansion to more terms. Okay. So, now the thing is, the ODE is stable if the real parts of the eigenvalues of A are all negative. In other words, so what this means is the solution will decay to 0 as t goes to infinity. We do not want the solution blowing up. So that requires the real parts of the exponents to be negative. Because so this would ensure that the exponentials of those would be less than 1. So that way we do not have a solution blowing up on us. Okay. So what about the numerical method? So if a method is stable, if the eigenvalues of m are less than 1 in absolute value, so that we get the same behavior, that the numerical solution is not blowing up. Okay.
Wait, they're less than 0 or less than 1?
Less than 1,
Okay.
because m is approximating the exponential.
Okay.
Yeah, so this is what we're really after, to mimic this behavior. So, what about forward Euler and backward Euler? Are they stable? So at least with these methods, it's not difficult to check. So for forward Euler, m is equal to identity plus a delta t. So that means that each eigenvalue of m is equal to 1 plus eigenvalue of a times delta t. So that means that absolute value of 1 plus lambda I delta t, I'm being lazy for my notation here, is, so I'm getting rid of the of a part, is less than 1. But if I expand that out, and then I subtract 1 from all sides, okay. So this imposes a restriction on delta t. So delta t has to be less than and the eigenvalues of a already have negative real parts. So that's taken as a given. So if a has particularly large eigenvalues, delta t must be particularly small.
Can you say that again?
Okay. Notice the inverse proportionality. So large eigenvalues of a lead to a small delta t to ensure stability.
So basically, if the eigenvalues of A are small, but delta T is also small, then it's not stable. Or is forward Euler always stable because of that?
What I'm saying is, since a is something that's given, you consider the maximum, the largest eigenvalue of a, to see how small delta t must be. So as long as you have your delta t that satisfies this, then you're okay.
So you pick the delta t to ensure
Yes.
stability.
Yes.
Okay.
But here's the thing. When this system of ODEs comes from a PDE, you're going to get large eigenvalues. It's just something that always seems to happen. And in fact, the more grid points you use in your spatial grid, so the smaller your delta x or your h, the larger these eigenvalues get. So as delta x goes to 0, the eigenvalues the largest eigenvalues go to infinity. Therefore, delta t must also go to 0 with it. And in some cases, delta t is proportional to delta x. That's bad enough. But in some cases, it's proportional to delta x squared. So it's really small. So this is why time stepping is a problem with PDEs. Because now we have more powerful computers, so we expect more realistic simulation. Therefore, we use finer spatial resolution. In other words, smaller delta x. So we need smaller delta t. So people are thinking, oh, these super fast computers that we have now can simulate more efficiently. And it's like, well, actually, no, they can't. Because they're taking more time steps due to the increased resolution. So we're not really gaining anything. Yeah. And this is why I'm so gung-ho about rethinking time stepping. And I'm still waiting for people to listen to me. So, well, some are. Just not the people who give out money. Working on it. So that's forward Euler. And explicit methods tend to have this kind of restriction. Now, what about backward Euler? So I'm going to have this situation. 1 over 1 minus delta t lambda I, an absolute value, must be less than 1. But here's the kicker. Lambda is negative, or at least has a negative real part. So if it's negative and a negative, we have a larger denominator. So it is, actually I'll use a proper term here, unconditionally stable. So you can choose delta t to be as large as you want. May not get much accuracy, but at least your solution will be bounded. So certain implicit methods have this property of unconditional stability. Not all implicit methods, like certain high order implicit multi-step methods, run-kind methods, those will still have some kind of stability restriction. But generally with implicit methods, you can get away with a larger delta t. And that's why I had a pro and con earlier, where yes, implicit methods have more expensive time steps, but you take fewer of them. And here's a simple example to show why that's always true in the case of backward Euler. Okay. All right. And a quick example about stability. Let's suppose we have ut equals uxx. So that leads to a system of ODEs. Y prime is equal to ay, where A is the same old center difference matrix that you're probably sick of by now. Okay. Well, let me make sure I have all this for Jessica. Okay. All right. Now, the eigenvalues of this matrix are known. The eigenvalues in absolute value are less than 4 over delta x squared. But the eigenvalues are also negative. So what that means is this is a negative definite matrix. Therefore, positive definite. Yeah. So in other words, A is negative definite if minus A is positive definite. So it's stable if, similar inequality over here, 1 minus 4 over delta x squared, so this is the lambda, times delta t is less than 1. But based on this inequality here, that would mean that delta t must be less than 2 over this, so delta x squared over 2. So I should say this applies to forward Euler. Okay. So that is an incredibly strangling time step restriction. So if I increase my spatial grid resolution by a factor of 10, I must cut the time step by a factor of 100. So that's why people generally don't use explicit methods for something like a heat equation. Wave equation, delta t is proportional just to delta x to the first power, so it's not so bad. Okay. Whereas backward Euler will be unconditionally stable for this equation. So I've been able to prove my k-test methods are unconditionally stable for certain types of problems, and we hope to extend that a little bit. So it's an unusual case, but and certain spectral methods have that property, but spectral methods have their limitations. Okay, I didn't mean to take up this much class time. I have covered everything. So, okay, unfortunately, yeah, we only have 10 minutes left of our regular class time. Now, if anyone has some homework questions, or what I can do is I can give some preemptive comment on problem number, it's the Fourier spectral one, which is number 5. Okay. Yeah, because you're about to get to that, right? And I think Jessica was too. Yeah, because I haven't really talked about, well, problem 5 is like problem 4 in the sense that you start out by doing a finite difference, and you're kind of used to doing that by now. It works exactly the same way. But I want to say a little something about part C. Because that's the part where you're doing something that you haven't done in previous problems. Okay. Okay. So 5, or even 5, not S now. 5C. So a problem we're solving is usual minus 2xx is equal to f on 0 to pi. And you have periodic boundary conditions. So u and all its derivatives at 0 is equal to u and all its derivatives at 2 pi. So this is going to become a typical system of linear equations, a u is equal to f. So f will be the function that you're given in part D, and evaluated at equally spaced points. So what I want to talk about is what is the matrix A in this case. Now, it is given in the notes. Okay. Okay, spectral. Okay, so A is equal to minus dn squared. So dn is the differentiation matrix, not for Chebyshev now. It's one for periodic boundary conditions. So this is taken from page 23 of the notes. Okay. So it has this form where you have 0 on the diagonal, and then you have, like on the subdiagonal, you have all elements on each diagonal the same. So 1/2 cotangent of h over 2. And then on the opposite diagonal, the subdiagonal, you have minus that. And then as you go to further diagonals, you have 1/2 cotangent, should be a minus. And then you have plus and 3h over 2, and then etc. So those are the values that you have on every diagonal. Now, so if a formula that you want is, okay, dn row j column m, okay, is equal to 1/2 minus 1 to the j minus m, cotangent. This formula is given on that same page. Okay, so that is what you use. And this is for j not equal to m. Otherwise, it's 0. Now, because of a structure of this matrix where you have entries being the same on each diagonal, like this one, like you created this one using SP diags. You can do that here too. You just have a zillion diagonals. You'd have to create them using a loop. What you might feel like doing instead is just having a nested for loop that loops over j and m and just uses that to fill in all of the off-diagonal entries. Okay. And okay. And what should happen, because you can figure out for in part D, the f you're given, you can figure out the exact solution. Because you're supposed to do an error analysis again. And I mean error analysis is in MATLAB, not Taylor expansion. Where you, again, try different values of h and see what the order of accuracy is. Now, for finite difference, it should again be second order accurate. For spectral, it should pretty much nail the exact solution. Because this is exactly the kind of PDE that spectral methods were built for. So in fact, you should find that the error is so small that it can't even really measure the order of accuracy. It's just round off. So that's the kind of error we like and rarely get. Okay, although that did happen in the periodic function of a trapezoidal rule, so in class last night. So okay, so that's a rundown on what to do for that problem. Okay, now I've never got to the point of saying anything about problem 6. I mean, there's a fair amount in the hints there, and I've talked about the recursion part, which seems to be what people have most trouble with, even though in terms of actual coding, there isn't very much to do. So what you could do there is go through the hints. So here's what I will do. In the interest of helping to manage stress, or hopefully reduce it. So if you feel so overwhelmed by what's going on during the rest of the semester that that problem 6 just seems like ugh, then what I'm willing to do is, if you decide to just not do that problem, then you can, but you do the rest of them, then you can just take an A- and go, and not touch that one. Whereas, or you can go for it with problem 6 to claim the A. So something for you to weigh there. we'll see how things go. At least getting everybody through problem 5. Okay, so any questions at this point? Okay, so everybody will finish everything really easily. And we all live happily ever after.
I feel like we can get 3 more.
Well, that's right, because you're suffering from 771, and you're suffering through. Okay, sorry, my final. Okay.
But after that.
Yeah. Okay, so tomorrow's a day of misery for. Yeah. Okay. Yes. Okay. Alrighty.